first. So we basically planned to talk about nonparametric regression, and we decided that we first try to understand the simpler model, which is referred to as the normal means model. And it's an example of a high-dimensional or non-parametric model, which is the simplest possible, essentially. And many interesting problems can be reduced to this model. The idea is that we observe a sequence of Gaussian variables where the mean is dependent on the index. So observation yi. So the simplest way of writing it is just that yi is normal, which means theta star I, and variance sigma squared I. Okay, and these are independent. They're not IID because the mean depends on the ith index. And you can write it in vector form as y is equal to theta star plus sigma w. So the vector form of this is just y is normal between vector theta star and variance sigma squared in. So the point was, if we want to do estimation, if you want to estimate theta star without any constraints, you do maximum likelihood. For example, you end up with just y itself. So if you maximize the likelihood, which is equivalent to minimizing the deviation of y from theta in the norm, L2 norm, you get y. We talked about the fact that there is still, in this case, just like we pointed this out, that there's the James-Stein phenomenon here, which allows you to actually do better than this without any extra assumption if you work with the quadratic laws. But it's not like a huge. So in terms of the, let's say the scale of the error still scales like n. You can do better, let's say strictly better, but this is still not a good estimator in general, because as n grows, this is going to grow with n. So if you want to do consistent estimation in some sense, you have to impose some condition on theta star. So the advantage of this model is that the complexity of the problem is incorporated into the structure of theta star. So we assume that theta star is in some theta, capital theta, and then the whole point is to try to relate the geometry of that set theta to the performance of estimators. So a natural estimator in this case is this restricted MLE, which is just the least restricted or constrained least squares estimator. You can think of it as a projection estimator because you're finding the closest point in theta to y. If, for example, theta is a linear space, this is just the usual projection. If it's a convex set, it's still a valid projection. But generally, you can think of it as a projection problem or a projection estimator. So the question is that what is the performance of this projection estimator, and sort of how you can understand this in terms of the properties of this theta so that we can design good thetas, let's say. Or in a problem, if you have a particular theta, what can you say about the performance? So we introduce some notations. There is basically this notation, which is of concern to us. So this is saying I'm going to shift the theta to theta naught by subtracting theta naught, and then I'm going to intersect with a ball of radius u around 0, which is effectively intersecting with a ball of radius u centered at theta naught if you look at the original theta. So we look at this and we saw that we had this result which related the deviation between theta hat and theta star, or the deviation of theta hat and theta star, to the Gaussian complexity of this basically neighborhood of theta star in capital theta. And the Gaussian complexity was this quantity. So for a set, the Gaussian complexity is defined as the expectation of the supremum of this absolute value of the linear function of theta, where the norm of the linear function is a Gaussian vector. So geometrically, it's easier to understand the width, which doesn't have this absolute value. And we talked about that this is measuring the average width in direction W, average being averaged over all the W's that you get randomly by picking from this distribution. We did some calculations, for example, for the L2 wall, the width is root D in D-dimensional space. For the L1, it's root log of the order root log D. So you can see it has a nice sensitivity to how big these are in high dimensions. So it's like a simple way of seeing that this ball is much smaller than this ball in high dimensions. There are interesting results in high dimensional probability book. There's another result that that the HTP has that tells you this is an effective sort of dimension. It's a better notion of dimension. It's more robust to variations of. So if you like move in, like if I add one more, if I sort of let's say extend this set in like another direction, which is orthogonal to this in a little bit, like the usual dimension just jumps to like 3. But the Gaussian width sort of gradually increases. So it's a more robust notion of dimension. So there are interesting results in that book. If you're interested, you can take a look. So what we're doing here is we're relating Gaussian width or Gaussian complexity of this neighborhood of the truth to the performance of the estimator. And so in order to understand this result, we have a result which depends on this radius u. And what we can do is we can try to choose u that is basically optimal in a sense. So there is a trade-off. So this term is going to go down if I increase u. This term is going to go up. And so we're going to balance the two out. By balancing, you can just set them equal and then solve for u. There's a slightly better way of doing it to also take care of this issue that's there. So what we do here is we state this result. So let me go on like to the next batch of slides because I have that. So let me copy this. Move to the other one. Okay. Yeah, so let's say you have this guy here. Let's do it here. So the point is, like a technical way of doing this, finding this is to define. We did the calculation. You saw that sort of we have to basically set this equal to this roughly. But what we do is that we define it to be like that. Find u such that this inequality is satisfied. If you have any u that satisfies this inequality, then that bound translates to this. So let me do the argument there. So if we have this inequality, then what do we get? So this is, so if you recall, GU is this. So GU T is gamma theta theta star U plus TU. So I just want to bound these two. So 2, let's say 2 sigma gamma U. This is the first term. So this is going to be bounded by, so if I multiply this to both sides by 2 sigma, I get kappa U star. And then I also have this, which I get like plus 2 sigma TU. Okay. And then if I divide by U, you can see if I divide by U, the U goes away. I would get kappa U plus 2 sigma T, right? So this term is bounded by that. The other term, so it's the maximum of the two term, is also going to be like this. So the other term is root 2 sigma GUT, which is going to be root bounded by root this guy, twice that. So you get 2 kappa u plus 2 sigma tu. There's an extra u missing here. So I wanna argue that the second term is bounded by this. Why is that? Oh, okay. Yeah, sorry. That's true. So this is the top, right? So you get ku plus 2 sigma t u. That's what this is. Which is further bounded by root ku plus 2 sigma t. I can just repeat this here because what I'm doing is that kappa is bigger than 1, let's say. So this term itself is bigger than this. I'm just adding this so that it gets bigger. So what I would get is kappa u plus 2 sigma t. So this is also bounded by that. So this is not too this calculation you can do for yourself. It's not too informative. But just that if I have something that satisfies this, then I have this inequality from this bound. Later on, we'll prove this. And so what this is saying is that the dominant term would be this. So whatever you can think of u as a radius of that neighborhood. Whatever u satisfies this, that immediately controls the error. Okay, so the radius of that satisfies this is basically the size of the error with high probability. And so it's natural to define a critical radius that satisfies this inequality. A critical radius would be a u that's the minimum that satisfies this. So it turns out that this quantity, usually the Gaussian width of that neighborhood, usually grows slower than it's like grows like this, for example. The other term, which is so this grows like this. The other term grows like this. It's a quadratic. Okay, so there is a smallest place for which this gets like the first time that this goes above. That would be like your critical radius. We'll do that calculation soon, but that just, this is an interesting equation. It tells you something about the performance of the projection estimator based on geometry of the parameter space. Okay, questions? So let's do, let's say I can extend, hopefully assign this as an exercise you can use. You can integrate this. You can get an expectation bound from that. You can expect expectation bound, which is much simpler. You get rid of the t, so you get kappa squared plus u squared plus sigma squared. If you look at the expectation, the sigma squared is like the noise in the problem. You can get rid of this. This is the part that you can sort of control by choosing theta. Okay, and this is another version which before we get there, instead of kappa, so this was like, remember, I'm gonna let this kappa to be dependent on root n for reasons that becomes clear, or I'm gonna take it to be basically c root n, so that critical inequality would be like that. Then it's easy to see that just replace kappa with like 2 root n, you get something like this. And then if you look at the expectation would be the squared plus the sigma squared. And then if I divide by 1 over n, the result would be like that. So delta n is the, let's say, smallest solution of this. Okay, so delta n is the smallest solution of this. That delta n would satisfy this. So this is like a pair coordinate pair. Yes.
So like I said, like a conceptual question. So like all these theorems require us to have a data that is like covering the true.
Yes. Yes.
So like in some sense we have to like take the reasonable data that we're pretty sure we don't know the true parameters. So in practice, like, there's a trade-off between choosing.
Yeah, there are actually results that you could do, like there's a result that I haven't included. We can include this. So there's an approximation property. So whatever theta peak, there's a closest theta in theta star to the true theta. So you have to pay that price and then near that best approximation. So there's like this estimation approximation trade-off. You can do that as well. Yeah. Yeah, but I'm here assuming that the true theta is in there. And but that's a good point. It's something that we can definitely sort of expand or extend these results to. There's actually results in the HDS book about that. But let's try to understand this case first. Yeah. So you will see like the parameter spaces that we look at are usually quite big. So you look at all the Lipschitz functions, which is pretty like reasonable relative to the parametric assumptions that you always make. Just assuming that something is Lipschitz is sufficiently good enough. But if the function happens to be, for example, discontinuous, then you pay a price. So you try to like, this is like a nice trade-off between the approximation and estimation. Okay, any other questions? So the reason why this happens, I mean, it happens to be interesting is, like from this perspective, this delta n controls the pair coordinate pair. When we link it to the nonparametric regression, you can also see that this comes up like naturally. So this would be like the prediction error for us, like the approximation of the L2 error. So that would control the prediction error. So this quantity is, let's see what it looks like, for example, for a sparse regression. So if you accept this result, all we care about is this sort of inequality now. So let's look at an example. So suppose we have the usual non-parametric regression setup. In this case, you can think of it as a normal means model. So remember, y is x beta plus epsilon, and then epsilon is sigma squared, normal sigma squared identity. That would be in, right? So this is n by d, right? And so I can think of this y as normal between x beta and variance sigma squared. You can think of this as theta, right? So if you look at nonparametric regression, if you care about the prediction problem is recovering this mean rather than beta. So the prediction problem in regression or sparse regression is exactly a normal means model. So can you tell me what the parameter space theta is in this case? What is capital theta? What kind of space is that? That would be just the image of x, image of, yeah, right. So that would be actually true. So without any constraints on beta, that's exactly what theta is. So for example, if d is much smaller than n, this is a d-dimensional subspace of Rn. So it has more structure than just any vector in Rn, right? So for example, if this was like n was 100, d was 2, the usual normal means model just has like 100 degrees of freedom, but this regression just has 2 degrees of freedom, and the space is just the image of x. So going back to your question, that theta doesn't belong to this, that would be like a regression model in which the regression is misspecified. So that's sort of something that you usually don't worry about, like even in the linear regression. Yeah. But yeah, so that would be the case. The question is, what happens if D is like the problem is high dimensional? So what if D is like 500, n is 100? What would happen to this? So what is x as 4 rank? Sorry? Yeah. This here. So this is still true, but it's just simplified. So much smaller space than Rn if D is, let's say, much smaller than n. Let's say D is 2, n is 100. But for the high D case, where n is much smaller than D, or rather D is much bigger than n, and let's say x is full rank. So what would happen? What would be theta? Sorry? So theta is in Rn, because this is like n by d. So it would be an n-dimensional subspace of Rn, which would be the entire Rn. Right? So in this case, like we're back to the unrestricted normal means model, and you can see you shouldn't be able to do any good here without any more constraints. So that's where, again, we introduce some set of constraints. Didn't work, but so we're going to impose our constraints that, for example, in the high dimensional case, now this is P. Let's say P is much bigger than n. We're going to assume that theta is x beta, but beta varies in all S sparse vectors. And another way of saying it is just theta is the image of this L0 ball of radius s under x. So if you want to imagine what this looks like, to imagine what it looks like, let's say n is 3, p is, p doesn't matter, like p could be 100, s is 1. Okay, so what would this theta look like? It would be a subset of R3. Yeah, so that would be like, theta would be the union of these. So it's a union of subspaces, basically. It would be a union of all p choose S coordinate subspaces. In this case, 3 subspaces. So in general, it would be union of p choose S coordinate subspace. So you can see it's a much smaller subspace of, let's say, R3. And So let's say the true parameter belongs to this theta. And so theta star is x beta star for some sparse, S sparse beta star. Then we can try to use our projection estimator. So if you try to project theta to this, it's equivalent to finding a vector x beta where beta is in there. So you're basically solving this. You get beta hat, and then your estimator would be x beta hat, right? So that's the projection estimator. So the projection estimator in this case just solves this L0 constraint regression. You can also see that you're basically projecting onto these coordinates. Axis, it's a hard computational problem, but here we're not going to worry about that. We just want to understand what would be the performance of this estimate. So in order to understand this, I have to do the like centering around theta star and then put a ball of radius u, L2 ball of radius u. So if I do the centering, because this is x b0 ps, and this is like x beta star. So you can see that the centering would be effectively centering this ball around beta star and then image under x. Okay, so this is a linear transformation. And this guy belongs to the ball of radius 2s. So why is that? Beta star is in the original set. So this is S sparse. And this is the set of all S sparse vectors minus some fixed S sparse. This is at most 2 S sparse. So it's going to be a subset of a bigger L, like the L0 ball. And so I can say that this X is subset of X intersect with this. Sorry. So X, the image of X under this, I'm going to call this U. And then you can see, you can go through, when we go through the proof of this result, that instead of this theta sub star, if I have a superset of this, everything works. So if I have if I replace this with a bigger set, I get an upper bound. So I can work with a superset. So I'm gonna, instead of working with this set, which is harder to work with, I'm gonna work with this, which is containing that. And so I'm gonna intersect with a ball of radius delta around 0. So that's the set that I have to calculate. So this is the set. The set that we need. We need to calculate the Gaussian complexity for. So the thing that I have to verify is the star-shapedness of this figure set. So I have to make sure that this is star-shaped relative to the 0. So is this star-shaped? Why is it a star-shaped? This is still like the image of L0 ball, right? So it's something like this. You can see this is a star shape, right? And because this is in general a union of subspaces, right? So you can write this as the union of coordinate subspaces of dimension 2s. Each one of the subspaces is star-shaped, and the union of a bunch of star-shaped sets is again a star-shape. Okay, it's not convex, but our result applies to any star-shaped set. So we have to just compute the Gaussian complexity of this. So that's the set. If I want to compute the Gaussian complexity, I have to basically compute expectation W theta. Theta belongs to this U intersect B 2n delta. If you unpack this, this is basically x beta in U intersect B2n, where beta belongs to B0 2s, right? Because U is like that. And so that's what I get. So beta has to be in like the 2s L0 ball, and x beta has to be in the L2 ball, so that's the radius, and sorry, yeah, u is going to go away because so that would be like this. Theta belonging to u means x beta. It looks like x beta, where beta is in B0 P2S, and this is this itself belongs to B2 delta. That's what it looks like. Okay. Yeah, it's a little bit funny, but you can just write it down. It just this is going to be like Wx beta like that, and then I leave this as an exercise for you. This is a very nice exercise in calculating. So this is like a supremum of a bunch of sub-Gaussian variables, and you can use the tools that you learned to calculate this. And it turns out that this is going to be delta. So you can imagine it should depend on delta because the size of this depends on delta. So if this gets smaller, this should like linearly vary with delta. But the interesting thing is that you get root s plus root log n, where n is p choose 2s. Okay, because you're sort of basically considering what you're going to do is that this is basically a union of this many subspaces. So you work with each one, and then you take the you know that like a maximum over a bunch of things is like root log this for sub-Gaussian. So it's a very good exercise for you. You show this, and then we have a bound P2S is bounded by EP over 2S to the 2S. That's the bound that you get for binomial coefficient. The E is like it's like you know, 2 point whatever. I'm going to ignore the E here and 2 here, so you get P over S to the 2S. 2 I'm going to also ignore. So if you take the log, so this is saying the log P2S up to constants is S log P over S. That's what you get here. So this is going to be root S log P over S, and this is bigger than root S. So I can absorb the first term into the second. So this is dominant, so I get S log P over S. So you can see the Gaussian complexity of this, although it's in a p-dimensional space, it is caged like root S and logarithmically in P. Okay, this is a subset of RP. Oh, sorry, not RP. It's a subset of Rn. This is a subset of Rn, but the parameterization is in RP. So the dependence on P is logarithmic. The dependence on N, so actually the dependence on N is non-existent here. So the dependence on N is like absorbed into the delta. Yeah, so this is a subset of Rn. So you then expect it to be like big, but this is like root S delta basically if you ignore the log factor. Okay. It's a good exercise, you'll do this. And then our theoretical inequality says that I have to compare this to this quantity. So I'm going to do that. So what we're going to do is like gamma u delta, I'm going to compare it up to constants with, so you can write this, let's ignore the constants. So you can write it as gamma, I'm going to like u delta, which is an upper bound on this, is up to constants root n divided by sigma delta squared. That's like a quick little equation that you can use to figure out the rate. So that's what we're going to do. So we'll do this. This is going to be root n sigma delta squared. So I want to solve this equation. So this side I have an upper bound. So I'm going to plug in the upper bound. I want the smallest. So the smallest that satisfies. You can argue for yourself that things get bigger if I replace this with an upper bound. I'm going to do that. And then I get root n sigma delta squared. Right? So what happens is that one of these deltas cancel out. So I get delta is bigger than or equal to sigma root n root s log p over s. So I want the smallest delta, so I'm going to push it down. So delta n, the critical radius, would basically be up to constants. I would say like sigma root s over n log p over s. Okay. So what this is saying, if you plug it into that equation that we had, so this is bounded by this plus sigma squared over n. So just plug in delta squared, I get this is going to be sigma squared s over n log p over s. And you can see this is bigger than this term. So this is like the more dominant usually. This is the baseline. This is like the parametric rate. Usually in these problems, it's like absorbed. So this is controlling the rate. So that's the rate. And you can see also that this is equal to this guy because this is x beta hat and this is x beta star. And if you recall, this is the prediction error in regression. So what you're saying is that if you do sparse regression, your prediction error goes down like sigma squared s over n plus this log factor. So this is the rate that you would expect if you did it in s-dimensional space. You're doing it high-dimensional space, but with s-sparse problem, so you get this, pay this extra log factor. Okay, and you can see it's pretty easy to drive this. From that result, it doesn't require you to do like basic inequalities. Actually, we do the basic inequality in recovering this result. But once you have this result and you like manipulate it to get this to this equation, you just have to calculate this Gaussian complexity, and this you'll do as an exercise. And you find out that the Gaussian complexity is like this. You plug it into the critical equation. That's the main point. You solve for data, it immediately gives you the right rate, and turns out to be the optimal rate. So you can do better than this. Does this make sense? Questions? Comments? Okay, so this is left as an exercise. Let's say this left. Mixer. Okay, so before going to nonparametric regression, so in this case you can actually compute this using the techniques that you know, but in function classes, it would be nice to have more like other technical tools that allow us to sort of translate certain estimates to this instead of, you can try to calculate this directly, but a very useful result is something called the Dudley's integral that connects the metric entropy to the Gaussian complexity. So if I can translate metric entropy bounds, which are the covering number bounds, to bounds on the Gaussian complexity, that you can use a lot of the approximation theory literature. Well, I'll have those at my disposal to sort of attack this problem. So that's the next idea I want to talk about. So there is this result called Dudley's entropy integral, stated here. Just want to see how many of you have seen this. Here, you see. Right. Okay. One. Yeah. So that's because we're working with the normal means model, you'll see the Gaussian complexity automatically comes in because the noise is Gaussian when you try to prove this. So there is no natural way of doing Rademacher complexity here. Rademacher complexity and Gaussian complexity are closely related. So Rademacher complexity is defined. So how is it defined? Yeah, so this would be like epsilon, the same thing. So this is like, let's go back up. This is the Gaussian complexity. The Rademacher complexity is like or Rademacher width, it has the same issue. So the width is a better measure than the complexity because it's translation invariant. So it's like that where epsilon is a vector of independent variety Rademacher value. Rademacher value was like basically uniform in ±1. The random signs basically. Okay, so this is also a random vector, and it measures the complexity. There's zero mean. There's a close relation, but there are some nice exercises in chapter 5 of HDS that compares. Maybe I should assign those exercises to compare these two. But this is very useful in empirical process theory because of the technique called symmetrization. When you try to, it's actually related to what we're going to do, but when you try to control supremum of things like this, minus the expectation of fxi. So this is called the Gaussian, this is called the Rademacher process. So if you take 231C with me, I'll talk about this half of the course. Like in learning theory, oftentimes you end up controlling things. And also in this case, we're going to get around that in the Gaussian, like normal means model, we can avoid this. But if you want to control things like this, this is some sort of a uniform law of large number. This is saying this is the empirical average is close to the population average. And if you want to control this, you'd introduce these independent variables is controlled by twice, I believe, something like 2 over, I have 2. So 1 over n summation epsilon I fxi, where epsilon i's are independent. You can see the connection to the Rademacher sort of business. So this gets rid of the expectation here, symmetrizes these deviations. And if I fix xi's, as f varies in f, this varies in Rn. So this is like the set T. So Rademacher complexity like naturally comes in here. It's a good question, but let's not worry about this for now. They're related. So we want to control the Gaussian complexity, and it turns out that the Gaussian complexity. So this is a version of it. Like a simpler version is just something like, I should have written that. So gamma t, which is expectation of supremum t in t. So this is the Dudley's integral. So if xt is a Gaussian process or a sub-Gaussian process, then this is up to constants bounded by integral, let's say 0 to infinity, root log n epsilon t and rho, where rho is the so-called metric of the process. So X is sub-Gaussian process if the increments are sub-Gaussian. So if this process is a stochastic process indexed by t, we'll say that it's sub-Gaussian or has sub-Gaussian increments if I look at an increment, the deviation of the process, the psi2 norm is up to constant bounded by some metric. So if I have something like that, then the covering number of this index set in this metric, which is this guy, and the log of it, which is the metric entropy, sort of controls the supremum of this process. This is called Dudley's integral. It's a very neat connection between the expectation of the supremum of a sub-Gaussian process and the metric entropy of the underlying set. So you can see there's some sort of relation between the stochastic processes and the geometry of the space. Especially, for example, a Gaussian, if xt is a Gaussian process, so this should be a zero mean, so expectation of xt. We're talking about zero mean processes. So this is sub-Gaussian increment. sub-Gaussian. So if you look at a Gaussian process, which is, so let me maybe do this earlier. What do I want to do here? Introduce these ideas first. So that's the general sort of Dudley's integral for Dudley's integral for some Gaussian processes, sometimes called a process with some Gaussian in, aka a process, a random process with sub-Gaussian increments. So a very special example is this process that if I define xt to be w times t, right? T is in Rd. Okay, this gamma t then would be expectation of supreme. That would be the Gaussian width exactly. So, which is also related to the Gaussian complexity. So this process, does it have some Gaussian increments? So can I? Right, sorry, W is Gaussian. W is our standard Gaussian. Can I claim that this has some Gaussian increments? Whereas T is like in belongs to T, which is a subset of Rd. Yeah.
Constant value of that. T minus S on the inside of the product.
Cauchy-Schwarz. Okay.
So T minus S is then your
metric. What we care about is not this is like a stochastic deviation. You can see this is random. I want to show that this is like sub-Gaussian, and this is sub-Gaussian metric, like the sub-Gaussian norm. So this side should be deterministic. Right, this side is not deterministic. You're close though, but can I claim that this thing, this deviation, this is the deviation, can I claim that this is sub-Gaussian? What is the distribution of this actually? Can you figure out? So if this is Gaussian, what is this? Gaussian because it's like an inner product of a Gaussian vector with some fixed. So what is the mean? 0, and then it's univariate. What is the variance?
T minus the log of T minus S.
Yeah, so that would be the mean and the variance. So now can I claim that this is sub-Gaussian? It's a Gaussian variable. It's definitely sub-Gaussian. So what is the sub-Gaussian norm?
To an absolute constant times the variance of those.
Up to a constant would be proportional to the variance, which is this, right? And so this is actually the square of the sub-Gaussian norm up to constant would be proportional to the variance. So the sub-Gaussian norm up to constant is this. So you actually prove that this is sub-Gaussian it processes of Gaussian increment, then this is the metric. This is the Euclidean metric, is basically the metric for this process. So if I apply the Dudley's integral, it would tell me that the Gaussian complexity of any set, like the Gaussian width basically of any set. I shouldn't call this gamma. This is general. So this, for a general sub-Gaussian process, this is just gamma would be this for this particular process. This is a linear Gaussian process. Okay, linear Gaussian process. So for this one, you would get, what do I get? Wt, this would be integral up to constants, integral 0 to infinity root log n epsilon, and then t, and then the L2 norm. So if I can control the metric entropy of t in the L2 norm, then I can use the Dudley's integral to control the Gaussian complexity. Okay, so this allows me to use metric entropy estimates to control the Gaussian complexity of a set. This is actually Gaussian width, but it's very much related to the Gaussian complexity. You can sort of argue a little bit what happens if I put absolute values here. Definitely, if t is symmetric, then I can do this. If it's not symmetric, there are other tricks. So you could look at t union minus t. So the Gaussian width of t union minus t is the same as the Gaussian complexity. So if you control the metric entropy of t union t, then it would work. Questions about this? So I'm not going to prove this. Maybe if you have time at the end. So the proof uses some idea which is called chaining. It is similar to the discretization argument that we used for controlling the operator norm, if you recall, but it's done at multiple scales. So instead of doing it once, you do it at different scales, and then you sum, and then the sum turns into an integral. It's a very interesting proof. If you get a chance, we could do it. I'll usually do it in 231C. But if you're interested, let me know, or you guys can pick up this as a project if you want. Not the Dudley's, because it's well known. It's related to the chaining argument. So chaining proof by chaining argument. By a chaining argument. So the version of this that I have here is, I could also write this as, for simplicity, I sometimes write it as n2 epsilon t, just saying that the covering number in the L2 norm of epsilon and t. So the version that I have here is slightly different. So that's the version that you usually see. Sorry. That's the usual version. The version we have is a slightly, so usually when you prove it for a finite t, although this is usually stated for a general t. If t is like uncountable, then you have to worry about whether the supremum is measurable, things like that. If it's countable, things are fine. But usually you can define this as the largest value that this can get as you vary this over the finite subsets of t. So that the problem is usually reduced to understandings for finite subsets. In any case, what we're going to use it is we're going to use it for a net. So I'm going to pick a net, a delta net subset within this set that I want to. So I want to control the Gaussian complexity of this. I'm going to pick a net delta net there in L2 norm. So this is like a discrete set of finite number of points. Then I'm going to look at the Gaussian complexity of that net, which is just this quantity, and this has this bound. So I can control the metric entropy of n, or this is an upper bound on the metric entropy of n, because this contains n. The point is that I can go, I don't have to go all the way to 0, although you can do 0 here. But if it's a delta net, I just have to go up to the radius delta. Because of the way that you prove, you end up constructing nets, and you stop when you hit like the resolution hits the set, then you stop. So you don't have to go all the way to 0. Although it's not gonna, we're not gonna use it, but this version is useful to remember. And the upper bound, you can also see here, you don't have to go all the way to infinity. Can you argue why you don't necessarily have to go all the way to infinity in general? Yeah, great. So if you have like a set, if this epsilon is bigger than the diameter of the set, you pick like one point, and you can just cover everything by a single ball. So if epsilon is large enough, a single point centered here would do, then n would be 1, and the log would be 0, and above which like it's 0. So this usually, it's written like that for simplicity, but it's sort of understood that you can always go all the way like to the diameter of the set, and then after that you stop. And here the diameter is sort of proportional, so you have to like, you can absorb things into the constant. The diameter of this is 2u basically. It's actually a ball. You can see if it's a set, is like, this is our set. If it's going to be inside a ball of radius u, right? If it's inside a ball of radius u, I just need a single point at the center of this ball of radius u to cover the set. So I have to just, it's enough to go up to u. So that's the form of the Dudley's integral that we're going to use. In fact, we're going to usually use it at 0 here. But it's just useful to remember. Okay, it's just a modification of this, but that's interesting. So the reason why I'm going to go up to a net is because of this fact that you're going to show as an exercise. So if I have, this is an exercise. So first, any questions about this? So just, you have to accept this for now. It's a very well-known result. It's in HDF and HTTP book as well. The proof in the HTTP is probably easier to go through, and you're welcome to check it out. And this is the exercise. So what we can do is that we can pick a delta net in T. Then you can show that the Gaussian complexity of T would be delta root n plus the Gaussian complexity of the net. So this you can do as an exercise. It's a very nice property of the Gaussian complexity. I'm going to pay a price at delta root n plus the metric entropy, sorry, the Gaussian complexity of n, which I can control by this. So let's combine these two facts. If I combine the two facts, then if I do this, theta star, theta star u, and this is a net, what I would get is this is going to be bounded by delta root n plus c times that integral, right? So that's the result that I'm reproducing here. So that controls the this bound controls for any. So the net is gone now, but you can see that. So this delta has to be less than or equal to u. So for any delta less than or equal to u, the radius, I get a nice bound like this. Okay. So let's see how we can use this. What I want to do is that I want to solve the critical inequality, which is gamma theta star u less than or equal to, there was like a constant here. I'm going to ignore the constant, root n over sigma times u, or you can say, yeah, that's basically, that's the critical inequality. The idea is that I can use this upper bound, just plug it in here instead and solve for that. So I can solve So let's see how it goes. Yeah, so it's a little bit tricky. So I'm going to take the okay. So unfortunately, this is a little bit tricky. So what I'm going to do is that this result holds for any u, for any delta. I'm going to replace delta with delta over sigma. Or sorry, yeah, delta squared over sigma. So I'm going to replace this with delta squared over sigma. This would give me delta squared over sigma. This would give me delta squared over 4 sigma. And then I'm going to take u to be delta. So I can take, so any delta less than u, usually delta is going to be going to 0. So delta squared basically is much smaller than delta. So I'm going to do this. I'm going to basically look at between this and delta. That's what I'm going to do. So this is going to be delta and delta. Then you can see that if I want to solve this equation, yeah, there's this delta squared. So that's the critical equation. If you go back, I'll have to solve this equation. And the way I constructed this side is of that order already. So it's just enough to require that this is less than or equal to this. Okay, so with the way that we constructed it, it's just the first term is already less than or equal to root n sigma delta squared. So it's enough to have c integral delta squared over 4 sigma, and then delta here. Sorry, should be delta. Root log into epsilon theta star delta d epsilon less than or equal to root n sigma delta squared. So that's the alternative equation that you can solve instead of the critical inequality. The way that we sort of worked it out, this piece is already controlled. Like we set things up so that this is already of this order. So I just need to make sure that delta is satisfying this part. Okay, so that would be the critical inequality in terms of the metric entropy. So that's the result that you get, which is a very neat result. So it's saying like within this range, the metric entropy, if you integrate it, it controls, the root of metric entropy controls this side, and then the other side is like delta square root. Does this make sense? It's a little bit tricky, but if you go through it, once you have this, then you reparameterize. This holds for any delta and u. You choose probably better ways of doing it if you chose different notation here. But we replace this with this and u with delta, and this equation holds. Okay, so now remember this, we'll come back to this. So this is the technique that you're going to use to control, like to understand the Lipschitz sort of class. Because if you recall, we talked about the metric entropy of the Lipschitz class, and I want to use that to drive the rate for that problem. Just have this in mind. We'll come back to it. So this is how you can use the metric entropy to write down this critical inequality, and then I'll give you an example. Any questions? Yeah, so this is, we'll come back to this. So let's go back to the nonparametric regression, see how this all fits in there. So as an example, we looked at, so like we started actually with this and looked at the normal means model, but nonparametric regression model is something like that, if you recall. So f star belongs to some class of functions, and so So the projection estimator in this model is just something like this. Okay, so let's see how we can translate this to nonparametric regression. So a natural thing to do is divide everything by, I'm going to divide everything by n. So I get f star xi divided by root n plus sigma over root n wi. And I'm going to call this theta star I. Okay. And this would be my new y, if you want, y tilde I, if you want. Right, and this would be my new sigma. This would be sigma tilde. So that's the setting. Y tilde is yi divided by root n, sigma tilde is sigma divided by root n. And if you want, you can think of this theta star as 1 over root n f star x1 up to f star xn. This is a particular map. So you can think of this as phi of f star. So it maps any function f to a theta star. And this map that maps f star to theta star is a linear map. So phi works from the function space to Rn. It is a linear map. So it's easy to see that if I add two functions, if I map them, basically I'm sampling them. This is a sampling operator. So it samples the function at those points. So addition turns into addition, scalar multiplication into scalar multiplication. That theta star that we had would be just the image. Yeah.
So it's like an evaluation path.
Yes, exactly. So evaluation, you can think of it as an evaluation. So individually, these are evaluation functionals. So like if you've seen like RKHSs, so f maps to f, let's say x1, this is a linear functional that is called something called evaluation functional. It evaluates all the functions at x1. This is a linear map, and this is just a collection of like a bunch of them. Right, yeah, so sometimes I'll refer to it as a sampling operator because it just samples the function as a bunch of points. So like you can say vector value evaluation map or sampling operator, whatever you want to call it. So theta star is nothing but the image of this function class under the sampling operator. So it's going to map, there's going to be a subset of Rn. Okay. And if f is like a vector space, for example, because it's a linear map, this is going to be another vector space. But in general, it could be like a complicated set here. And then this operation, this projection operator that we have seen here, if you look at it, the projection operator is f in f, 1 over n summation I from 1 to n, yi equal f xi squared. So I'm going to move 1 over n inside. I get summation I from 1 to n, yi divided by root n minus f xi divided by root n, right? And so argument f in f, so the equivalent version is just y tilde I minus, let's say, theta I, summation I from 1 to n, argument f in, you can call it theta star if you want. And then this would be theta hat. So here theta I is f xi root n for all I from 1 to n. And you can see theta is connected to f via that evaluation map, right? And then theta star is again, as usual, as before, this is like f. Okay, and the model is just y tilde is theta star plus sigma tilde w, where w is normal between 0 and n. So that's, and then this is just phi of F star. Okay, so this is exactly the normal means model. And you can see this is just the image of the true function under the sampling operation. And the usual, like least squares nonparametric regression is just the projection estimator. Okay, so we're back to the normal means model. And the only thing that, for example, I have to worry about is the complexity of this set near this point locally, and for which I'm going to use the metric entropy ideas. Okay, I guess we're out of time. Next time I'm going to come back and sort of just we have to like see how the metric entropies sort of translate. So what is the, so we care about the metric entropy of theta star in L2. What kind of norm does it correspond to in the F space? So there's a particular norm in the functional space that translates to the L2 norm here. And if you want to control the metric entropy of this in the L2 norm, it's enough to control the metric entropy of F in that norm. Then we can use those results and drive like what is the how well this performs in terms of how big the class is. Okay, thank you guys. See you next time. Yeah, thank you.